Chemistry powers today, but courageous chemistry is shaping our tomorrow. It's fueling the hydrogen economy and driving clean energy. It's in our semiconductors and even powers our 5G. It makes bridges stronger and medical equipment safer. Chemistry powers progress and binds us all together. But there's something more that sets us apart. Courageous chemistry.
Hello and welcome to today's lesson. In today's lesson, we'll look at application of electrolysis. Okay, now we know that electrolysis, or we know what electrolysis is already, is it not? Yes, electrolysis find a wide range of application in science, field of science. Okay, but we are going to look at the field today, and one of them is preparation of important substances such as chlorine, oxygen, sodium hydroxide, and then hydrogen as well. Okay, another one is electroplating. By electroplating we mean coating an inferior metal with a more superior metal. It's mainly done for or to prevent corrosion. Then we also have extraction of metals and purification of metals. We use it for extraction of metals from their ore. We also use it for purification of metals. All right, preparation of important substances. We know that the principle of electrolysis starts in movement of ions in solution. Now when these ions get deposited at the cathode, for example, they end up forming elemental substance. Okay, now when ions move away from solution or electrolytes, the residual electrolytes contain sometimes important chemicals. Also, the elements deposited at the anode and at the cathode are also important substances. You have to pause the video, go through the different electrolytes that are or chemicals produced after the electrolytic process, so that you understand this idea of preparation of important chemicals by electrolysis. So if we look at the table below, you will see that during the electrolysis of concentrated copper chloride, copper, which is a metal that is very important, is used in making wire, is deposited at the cathode, is it not? While chlorine, which is a gas used as a bleaching reagent or agent, is deposited at the anode. So in this case, you see that both the two substances are very, very useful substances. Now you look at the other one, copper sulfate. Again, we get copper, is it not? Yes, and we get oxygen gas. Of course, oxygen gas is very important. And then you have the third one, which is concentrated sodium chloride. We have hydrogen gas, and then we have chlorine gas. It will interest you to know that the electrolyte solution that will be left is sodium hydroxide, is it not? Yes, and sodium hydroxide is a very important substance. We use it to make soap, is it not? Whether liquid soap or the other soap. And then we also use it to neutralize acidic soil, is it not? Yes. We also use it in making soda ash, is it not? Soda ash is a very important chemical that is in making glass, from the survey process.
Electroplating is an electrolytic process by which a thin and compact film of a non-reactive or superior metal is deposited on an article made of a more reactive or inferior metal. Let us now see how an aluminium spoon, which is inferior, is electroplated with nickel, a superior metal. Electroplating is based on electrolysis. The article that is to be electroplated, here the aluminium spoon, is made the cathode by connecting it to the negative terminal of the battery. A pure nickel rod is made the anode by connecting it to the positive terminal of the battery. A solution of nickel ammonium sulfate in water is used as the electrolyte. When a current is passed, the nickel atoms from the anode lose electrons and enter the electrolyte as nickel ions. The positively charged nickel ions are discharged at the cathode by accepting electrons and get deposited as a thin film of metallic nickel on the aluminium spoon. Thus the aluminium spoon is electroplated with nickel. Purpose of electroplating: protection against corrosion, decorative purpose.
Electrolytic refining is the process of obtaining pure metals like gold, silver, copper, etc. by the process of electrolysis. Electrolytic refining of copper. Take an electrolyte of acidified copper sulfate solution. Take the anode as a thick rod of impure copper and the cathode as a thin rod of pure copper. Current is passed through the solution. As a result, the acidified copper sulfate electrolytic solution splits into copper ions and sulfate ions. The copper ions from the electrolyte get attracted towards the cathode. The copper ions gain 2 electrons from the cathode. And deposit as pure copper atoms on the thin copper rod. At the same time, copper atoms from the anode lose 2 electrons, get converted into copper ions, and dissolve in the electrolytic solution. Thus, the concentration of the electrolyte remains the same. In this way, indirectly, copper atoms from the anode get deposited on the cathode repeatedly. Hence, eventually, size of the anode decreases and size of the cathode increases. The reactions that take place at the anode and cathode are as follows. In this way, all the pure copper from the anode deposits on the cathode. The impurities in the impure copper rod settle down as anode mud at the bottom of the container.
In today's video, we're going to see how we can use electrolysis to extract reactive metals from their oxides by first melting them into their molten ionic compounds. As we've already seen in other videos, metals often exist as oxides, like aluminium oxide or copper oxide. If we want to remove the oxygen to isolate the pure metal though, then we're going to need to reduce the metal in the oxide, which is just the fancy way of saying remove the oxygen. Now, the cheap and easy way to do this is by reduction with carbon, where the carbon atoms displace the metal in the metal oxide to form pure metal and carbon dioxide. However, this only works for metals that are less reactive than carbon, like zinc, iron, and copper. For all of these more reactive ones, though, we have to instead rely on electrolysis, which is much more expensive because it requires loads of energy. As you saw in the last video, electrolysis is a process by which we can separate ionic compounds into their pure elements by passing an electric current through an electrolyte. So if our electrolyte was aluminium oxide, then we could use electrolysis to split it into pure aluminium and oxygen. The issue, though, is that electrolysis only works if the ions can move. But aluminium oxide is solid, so the ions are all fixed in place. And to make matters worse, it's found within an ore called bauxite. So before we can do anything, we have to somehow turn this solid bauxite into molten aluminium oxide. Because if it's molten, then the ions will be free to move around, which is what it needs to be considered an electrolyte. The first step is to purify the aluminium oxide from the bauxite that we mined from the ground, which you don't need to know the details of. Next, we need to melt our aluminium oxide to make it molten, which is actually quite hard, because it has a melting point of over 2000 degrees Celsius. So we first mix the aluminium oxide with a mineral called cryolite, which lowers the melting point. Even so, it still requires really high temperatures, and so loads of energy. So overall, we need to purify it, then mix it with cryolite, and then we can melt it. Now that we have our molten mixture, we can set up our electrolysis equipment. So we need some sort of beaker to hold our molten aluminium oxide, which remember is our electrolyte, and we need our two electrodes, which are made of carbon and act as conductors through which the electrons can pass. On the right, we have the positive electrode, called the anode, and on the left, we have the negative electrode, which we call the cathode. Then we connect these with a wire and some sort of power source, like a battery, so that electrons can flow in a complete circuit. If we take a closer look at our electrolyte of molten aluminium oxide, there will be oxygen 2- ions and aluminium 3+ ions. Because they're negative, the oxygen 2- ions will be attracted to the positive anode on the right, where they'll transfer their 2 extra electrons to the anode and be discharged to oxygen atoms, at which point each pair can combine to form an oxygen molecule and float off into the air. The electrons, though, will be passed through the wire to the negative cathode on the left. As it's negative, it will attract the positive ions in the electrolyte and can donate electrons to them. In our case, it will donate 3 electrons to each aluminium 3+ ion to form aluminium atoms, which will then slowly pool in the bottom of the beaker as molten aluminium metal. Now that we've seen what's happening at each electrode, we can work out the exact equations that describe the electrolysis process. Loss of electrons, and reduction is gain of electrons. In addition to these half equations, we can also write the overall equation for the electrolysis reaction. We start with aluminium oxide in liquid form, and we know this goes to form aluminium, also a liquid, and oxygen as a gas. So all we need to do is balance it, and it will look like this.
Welcome back from that interesting class. This now brings us to the end of today's lesson. Remember to do other activities in this lesson. See you in the next class.
There'd be no reason for crying.